Okay, so in this video we're going to talk about what is uninformed search and informed search, but mainly we're going to focus on what is uninformed search. So the name states that uninformed means that you're not telling the agent or the AI where to go or where to search or where is the goal, right? An informed search is more like guiding or giving hints to the agent where the goal is. So in this very, very poorly drawn example of Pac-Man that I just did, you can see, oops, my bad. You can see that when the Pac-Man goes to this point, or when it reaches to this point, it has two options. It can either go up and then go to a dead end, or it could go just straight through and then go up and then it will find the goal. But there is no guaranteed way as to how the Pac-Man could know where to go, right? So this is uninformed search. And in informed search, let's say there's like this ghost on the way on the path, and it's like telling the Pac-Man that you should go straight, and maybe that will lead you closer to a goal, right? So now without further ado, let's start with different types of uninformed search. In this video, I won't be talking about as to how you would implement different uninformed searches. Hopefully, if I get the time, then I might also upload videos, coding videos related to uninformed searches and hopefully informed searches. But without further ado, let's start with the first uninformed search, which is BFS. So let's take a look as to how BFS works. Now, the first thing that happens in BFS is generally it is also known as a level-wise search. Okay, so breadth first search is also a level-wise search. And what I mean by that is if you're starting with node A, then what you would do is you would go to the next level, which is, let's say if this is your first level, this is your second level, this is your third level, and this is your fourth level. You would traverse level-wise. So first you traverse A, then you're going to traverse B, then C, and then D, right? So I go from A to B to C to D, and then I would go to the next level, which is E to F and to G. And then lastly, I would go to H, right? So this would be D to E to F to G, and then finally to the goal, which is H. Okay, so that is breadth first search. How is it different from depth first search? Well, as the name states, it goes into a depth, right? And it goes down the rabbit hole. So you start with A, then you would go to B, then you would go to E. Now you can't go anywhere else, so you go back and you see, hey, does B has any other children? No, B doesn't has any children. Okay, let's go back. Does A has any children? Yes, it does. So you go down that depth. And then you go back, you go back, you go back, and you say, hey, does A has any other children? Yes, it has. So you go to D, and then to G, and then you go to H, and since you have met your goal, you just stop over there. So that is depth first search. Now I will be talking about the different advantages and disadvantages of BFS and DFS, right? But to give a very, very simple idea, BFS takes a lot of time to compute. And that's why it is better for shallow goals, which means the goals which are very near to the upper levels, right? And DFS is very good on memory. It's good on memory because since the traversals are being done on different data structures, for example, this one is being done on queues and this one is being done on stacks. So the overall memory that is consumed by DFS is smaller than the one which is being consumed by BFS, which means is that the space complexity of DFS is smaller than the space complexity of BFS. Also, BFS is a complete algorithm, which means that it is guaranteed to find the goal, whereas DFS doesn't guarantees to find a goal. And like I said, we will be taking a deeper dive as to why that happens in a little while. The next one is iterative deepening. And iterative deepening is basically the best of both the worlds, which is BFS and DFS. So like I said, BFS is more about completeness, right? And DFS is more about being memory efficient. So what it does is it takes the best of both of these worlds and it creates a new method, which is iterative deepening. Deepening states that it comes from DFS, which is depth, and iterative means anything which is repeated. So what happens is that if you're taking the same example, the way how this traversal works is that it goes to it traverses one level in every iteration, and it's like a depth first search for each incremental depth. What I mean by that is let's do a traversal and you'll understand. So first I go to the first level, which is A, and that's done. Is A my goal? No. Okay, let's increase one more level. So let's do the entire depth first search again. So I start with A, then I go to B. Okay, B is not the goal. So I go back. Is C the goal? No, C is not the goal. Okay, well, you go back. Is D the goal? No, it's not. So you can see this is still like a depth first search, right? But the only difference is that you're doing it over and over and over again. So in this one, you would go at A to B to E, and you can see I'm traversing A again. I'm traversing A, B again, even though I have done that over here and over here. But since it is an iterative process, we have to do it over and over again. So one could argue that yes, you are wasting a little bit of resources because you're doing the same thing over and over again. But if you compare this method with purely standard BFS and DFS, then iterative deepening performs a little bit better than BFS and DFS. So let's do this for one last time. We get to A, then we get to B, then we get to E, we go back, then we get to C, then we get to F, still not the goal, we go back, we go to D, then to G, and then to H, and we finally found our goal. So you did this 4 times. First you went to A, then you went to A to B to C to D, then you did A to B to E to C to F to D to G, and then in this one you did A, B, E, C, F, D, G, and H. That was the path. Then we have is the bidirectional, and the name states bi, which means there are 2 directions. And the way how we do this is instead of having a traversal starting from the start node to the goal state, we have traversals from both the start node and the goal itself. So in bidirection, you use either BFS or DFS, which means that in this traversal, let's say starting from the starting node, you can either apply BFS over here and over here as well, or you could apply DFS in the start node or this thing. So you have to apply both of them. Like if you're applying BFS, then the start node and the end node both should do BFS. If you're doing DFS, then both the start node and the end node should do DFS. So in this example, I will be doing DFS because that will take less time. And let's assume that in this traversal, we do the depth first search starting from the right position. So the way how we generally do this is first you start with the starting node, so it traverses A first, then it is the end node's turn, so the goal state's turn, so the goal state traverses H. So let me just write down the path over here so you can understand what I'm talking about. First it goes A, then it goes H. Then it's the start node's turn again, so I go to D. Okay, and then you write D over here, and then you start with the end node's DFS, so H goes to G, and then you write G over here, And then it is the start node's turn again. So start node goes to G. And you find that there is this common meeting point. In the earlier example, when I was doing it some other time, the meeting point was coming over here because I started with the end node first. But in this example, the meeting point is over here. And what this states is that you have finally found a path, which is AHTG, because if you have this kind of a traversal in which you're starting with two different start nodes, you can say in a way there are two different start nodes. You would find that in this way you can find the goal much more easily. So this is a bidirectional traversal, and basically the way how you stop this traversal is whenever you find a meeting point, you stop the traversal and you say, hey, this was the path which helped me to go from A to H. Okay, so now let's do uniform cost search. Uniform cost search also works on minimum path, which means the minimum cost. And what I've done over here is I've created a very small table, and this table will actually help you to solve the problem much quickly. So uniform cost search is always applied whenever you're talking about path cost or whenever you're talking about minimum path. It is also known as a variant of Dijkstra's algorithm. For people who don't know what Dijkstra's algorithm does, is basically it calculates the shortest path from any one node. So the shortest path. And the difference between a uniform cost algorithm and a Dijkstra's algorithm is, in Dijkstra's you apply this on the entire graph for all the nodes, and uniform cost is applied until you find the goal, right? So if you find the goal very quickly, you don't have to traverse all the other different remaining nodes, which you will see in this example. So the way how we do this is initially you start with your starting node. So in this one, it would be A, and then you would go to your next smallest node. So in this one, you have two options. You can go to either B or you could go to D. So I'm just going to write this down. I can go to B from A with a cost of 1. So 1 comma A, and I can go to C with a cost of 3 from A. I can go to D with a cost of 1 from A, and I can go to E, F, and G, and H as of yet, because I don't know if there is a path or not. But as of now, I have 3 options. And if you're doing this alphabetically, let's just choose B, right? Let's just choose this option. Let's just choose B, and we go down this point. Now, in the next step, right, this opens up the node, the path to E. So I'm just going to write this again, 0 comma 0. This is already traversed, so we're not going to traverse this one again. We have 3 comma A, we got 1 comma A, and now I have E. And now you have to remember that you have to also accumulate the cost. So I have 1 from A from B. So now this is going to be taking you a cost of 10 plus 1 from B. So this is going to be 11 comma B, right? And now you're going to see, hey, which cost is the least? And in this case, we will find that it is this one. It is this one, which is the least one. So we're going to choose this cost, this path. And this opens up the path to G. And now we have 0 comma 0. We got 3 comma A. We're not going to choose this one anymore. This is 11 comma B. We don't have F. We have G. And the cost of G is 1 plus 4. So I can go to G with the cost of 5 from D. And this is infinity again. So now which one are we going to choose? We're going to choose the one which is the least, which is this one, the C one. So we have this one chosen. And now this opens up H. This opens up F. So we have 0 comma 0. This is done. This is done. This is done. This is 11 by B. F is how much? 3 plus 8. That's also 11. So 11 from C. then I have 5 comma D, and then I have infinity again. So we're gonna choose this one now because the least one of these three options is 5 comma D. So we go over here, and this is now 5, and then we can go to H with a cost of 4 plus 1 plus 1, that's 6. So this opens up H with a cost of 6 from G. And in this options, we can see we have 11, 11, and 6. We're obviously going to choose this one. And when we're going to choose this one, we're at the goal state, and we're going to stop our algorithm. And as you can see, we didn't traverse E and F. So this was uniform cost search. Now let's talk about why uniform cost search is not optimal. And what optimal basically means is that it will always find the goal. It will always find the goal first, right? This is not optimal, and the reason is because, let's say if I have an example, for example, A, B, C, D, E, and F, and I have G, let's say H, and then my goal state is over here, and every single path cost is like 1, and this is like 2, and this is 1. 1, 2, 2. Let's say that this is like something like 8 maybe. So what happens is that you start with A, you go to B, you go to C, right? So 2, 3, 4, 5, 6. Now this shows you like 6 to get from A to F, and then you have to go all the way back, and then you can go to H, and then you would go to G, right? And you can see this is very inefficient. So you could have just chosen this path, which was 2 plus 8, which could have gotten you to the goal much faster and much quickly, but instead you chose this. You got really greedy, right? Really greedy in terms of this path cost. And that's the reason why your uniform cost search isn't optimal. We have BFS. Okay, let's just summarize this first. BFS is a level by level traversal. DFS is a depth first search. Iterative DFS is just apply DFS on each level. And it is the best of both the worlds of BFS and DFS. And bidirectional is where you start with the starting node as well, and you start with the goal node as well, and it's your choice if you want to apply BFS on both of them or DFS on both of them, and you're gonna stop whenever you're gonna have a common intersection point. And uniform cost search is just going to be based on the path cost. You're always going to choose the minimum path cost. Yeah. So let's start with this table. BFS is complete. Yes, complete means you're always going to find the solution. DFS is no, it's not. It's not complete because there could be a scenario where you could have an infinite cycle. For example, let's say A, B, and then it's a loop over here, and then you have C over here, and then you have G over here. So you have this graph, and you want to make, let's say you want to make a search tree for this. So you would start with A, then you would go to B, and then you would go to A or C, and then you would go to B again or A again. And if you go down this rabbit hole, you would find yourself to be stuck in an infinite loop. So it's not always optimal. DFS is not always optimal. I don't remember what this was. ID. Oh, it's iterative deepening. My bad. Yeah. Is iterative deepening complete? Yes, it is, because it takes the best of both the worlds. So if BFS is complete, and iterative deepening will always be complete as well. Is BFS optimal? Yes, it is always optimal, because if the cost is 1, then it is optimal. DFS is not optimal unless you have your goal is towards the leftmost. It's like towards either the leftmost or the rightmost. The goal is either towards the leftmost side or the rightmost side, then it would be optimal. Otherwise, it's not optimal. Iterative deepening, if BFS is optimal, then of course iterative deepening will also be optimal. So I'm comparing these three first, and then I will get to the bidirectional and uniform cost afterwards. So then we have the time complexity. Right, so the time complexity of BFS is O B of D. B represents the number of nodes in each layer. So if this is 1, then there's 3 nodes here and then 3 nodes there. And then you have 1 node over here. But we're always looking at the worst case scenario. And in this case, the worst case scenario is if we have 3 nodes in each layer. So you have 3 to the power of number of layers. So you have 1, 2, 3, 4. You have 4 layers. So this would be your time complexity. Similarly, you have the same time complexity of DFS as well, and also for iterative deepening, but the difference comes in space complexity. Like I was talking about, in BFS you have O of BD, but in DFS it's O of BD. Like this is to the power and this is multiplying. So this is much smaller than this one. So therefore, iterative deepening also adopts the space complexity of DFS. Then the data structure which is used, BFS uses queue, DFS uses stack, and since iterative deepening is a form of depth first search, it will also use a stack as well. Then let's talk about bidirectional searches. Is it optimal? The first is complete. Is it complete? No, it's not complete. If you're using DFS, it is complete if you would be using BFS. Is it optimal? Whoops, where did the P go? Is it optimal? Yes, it is optimal. It will always give you the shortest path because, again, if you're applying BFS with a cost of 1 and you're applying it on both the sides, you would always find the best path. Okay, what is the time complexity? It is O of P divided by 2, and this is only the case if your graph or your path is divided into, let's say, 2 equal sections. And what I mean by that is, let's say that you had a graph something like A to, say, to B to C to D to E, right? And you had G to, let's say, F, and whoa, my graphic tablet decided to go crazy over there. And let's say, let's do this, right? So let's say that you were going to A, you went to B over here, you went to C over here, and similarly you went to G over here, to F over here, and okay, so I can't go in this direction, so I'm locked over here. I can't do anything else. So what happens over here is I get to D. Instead of going to F, I go to D, and then I go to E. So what I accidentally did was I traversed the entire graph, and then I would go back to F. And in this case, you can see that I was technically applying the entire depth first search, and there was no meeting point halfway through. So if you have a graph something like this that we had in this case, in which you had some sort of an equal, somewhat of an equal traversal, that is, this one took like three node traversals, and this one took like 2 node traversals, then you would say that the time complexity of this is almost O of P divided by 2. And the space complexity would also be the same thing. You can either apply Q or stack. If you're applying Q, then it states that this is the BFS. If you're applying stack, then it states that it is DFS. Okay, uniform cost search. Is it complete? Yes, it is complete if there's no negative cost. Is it optimal? No, it's not optimal, and we just saw why it wasn't optimal. Do I have the graph? I don't have the graph, sorry. But you can go back in the video and you can see why is it not optimal. But its variant is, which is A star algorithm, and it is an informed search algorithm, and we will be looking at what an A star algorithm is in the next video. What is the time complexity of a uniform cost search? And it is basically C star divided by C, and C star is basically the actual cost, or like the minimum amount of cost it would take you to go there, and divided by the cost that you were getting. So for example, in this one, you went from 1 to 4 to 1, right? So the entire cost of this journey would be 1 plus 4 plus 1, and that would be 5, 6. Instead of the journey that you took, which was over here as 1 plus 3 plus this whole thing, so 6, and that's about 10. So 6 divided by 10, right? So that is O to the P to the power that thing. And the data structure that we are using in uniform cost search is going to be priority queue. Okay, so as we discussed, the advantages of BFS was that if the goal is shallow, if it's lying very close to the initial levels, then BFS is very good. It provides the shortest path or the shortest solution, right? Because if it's shallow, then it's effective. The advantages of DFS is that if it's better on memory because of space complexity of PD, and if there are multiple goals on the depth. So what I mean by that is, let's say if I have one goal, one over here, another one over here, another one over to another depth, then DFS could be also very beneficial. The disadvantages of iterative deepening is, as I discussed, there is a lot of repetition, but comparatively it performs better than BFS and DFS. So in short, that was all from this video, and hopefully I will see you in the next one for informed searches. Thank you.